Hi, my name is Abigail, and this is my Physics Lab 4 on oscillation. So the purpose of this lab in the introduction is to compare an actual spring oscillation to a computational model using both the tracker software and glow script code. In this lab, I used the provided video from the instructions and the initial conditions from the pre-lecture video, which I'll discuss in a moment. And the system today will be the Earth, the spring, and the mass. So, because everything is considered in the system, nothing will be considered as our surroundings. So the main physics concepts in this lab today are just the energy principle, which you can see here, and then that delta E is equal to, or the change in energy is equal to the change in kinetic energy plus the change in potential gravitational energy plus the change in potential spring energy. And then I also included the different equations to find kinetic and potential energies, which are that the kinetic energy is equal to 1/2 times mass times velocity squared. Then potential gravitational is just equal to mass times the acceleration due to gravity, which is 9.8, and then times the height. And then spring potential energy is equal to 1/2 times the spring constant times s squared. And S is equal to the length of the spring minus the relaxed length of the spring. And then Newton's second law formulas I also included. So the velocity update formula, which is final velocity is equal to initial velocity plus F net over m times delta t. And the final position is equal to the initial position plus the average velocity times delta t. So the initial conditions, as I said, they're from the pre-lab video. Of course, G is always equal to 9.8 when close to the surface of the Earth. The spring constant is 6.83. L naught is 0.123. And then you can also see, I'm going to talk about that in the next part, but L is equal to the ball position minus spring position. L hat is L divided by the magnitude of L. And S is equal to the magnitude of L minus L naught. And you can also see how I initialize K, the potential gravitational energy, potential spring, and then the original E. And on the right, you can see the ball mass, which was also provided in the video to be 0.402. And then the initial conditions that I found from my tracker are 0.168 and negative 0.776 for the Y. And initial velocity I considered to be 0. So here's the rest of my computational model. You can see that I included what the force of gravity was, force of the spring equation, net force equation, and then this next part is where I used Newton's second law and the momentum principle to find ball velocity, ball position. And then you see at the very bottom of that, update the spring with the same equations I mentioned earlier, and then calculate energy changes, which is where we find the new K, but we also find delta K, delta UG, delta US, delta E in this part as well. So these are my results. You can see on the right are the red is the experiment and the blue is the model. You can see there are some discrepancies, and I really think that these errors are from Tracker, and it was glitching a little bit, so I was just playing around with Tracker and trying to get that to work, but it's pretty close, and as close as I could get it. And then on the left, you can see the change in energy versus time and how delta E stays 0, and you can see the oscillations, and we're going to talk about those in just a minute. So here for the discussion, the what does it mean questions. The first one was for your model system, is the energy principle satisfied? And you can see from the top left that the energy principle is satisfied because it shows that when there's no work done by the surroundings, the change in energy is 0 because all the different parts of the system will add up to be 0. And you can see the delta K, delta U grav, and delta U spring, they all cancel out to be 0. And then question 2 is using the data you obtained in Tracker, make 2 separate estimates of oscillation periods. First by estimating the period of oscillation from the X position, and then also from the Y position. So looking at the X position, I found that the oscillation period was 1.519 seconds, and looking in the Y position, I got that it was 1.330 seconds from this data you can see on the bottom left. And the difference between the two is most likely part of my source of error, which I talked about just a minute ago. That tracker, you can see it should be perfect in some places, but it's not. So it's mostly my part, but either incorrectly tracking the center of the object in Tracker or another force that we did not take into consideration today, like force of drag or force or other external forces.